Fatty acids can be either saturated or unsaturated. A saturated fatty acid is one that has a hydrocarbon tail, composed of only single carbon-carbon bonds. This tail is fully saturated with hydrogen atoms, meaning that it contains the maximum number of possible hydrogens for a chain of its side. In contrast, unsaturated fatty acids contain at least one double carbon-carbon bond, and therefore have fewer hydrogens than a saturated fatty acid of the same length. Monounsaturated fatty acids have only one double bond, whereas polyunsaturated fatty acids contain two or more. So simple enough. But where fatty acids start to get really complicated is in their nomenclature. If you think about it, there's quite a bit of information for the name of a fatty acid to convey. The number of carbons in the chain, the number of double bonds, and the position and orientation of these bonds. This would be plenty to deal with under a single system of nomenclature, but to make matters even worse for us, multiple such systems exist. And many fatty acids, like linoleic acid, have common names that fall outside any of these systems. Fortunately, you don't have to worry about memorizing the common names of fatty acids, but you should understand a few of the systems of nomenclature. First is IUPAC nomenclature, which you might recognize from organic chemistry. When naming a fatty acid, the IUPAC method numbers the carbons in its chain beginning at the carbonyl carbon. If the chain contains a double bond, it's designated with a number, the number of the lower numbered of the two carbons taking part in the double bond. This system also incorporates EZ nomenclature, and for fatty acids, this is simple. Z corresponds to cis double bonds and E to trans. For example, palmitoleic acid is a 16-carbon fatty acid with one cis double bond at carbon 9 of its structure. In the IUPAC system, it's called 9Z hexadecanoic acid. Now, omega notation is a completely different system that is specific to fatty acids. It's unusual in that it counts carbons from the non-carbonyl end of the fatty acid. You can remember this because omega is the last letter in the Greek alphabet, so it indicates that we should start counting from the last carbon in the chain. In this system, palmitoleic acid would be described as an omega-7 fatty acid, because if we started counting at the non-carbonyl end, we'd hit the double bond at carbon number 7. You may have heard of omega-3 fatty acids and omega-6 fatty acids in mass media, and this is because these two groups of fatty acids have largely opposite effects on signaling pathways that modulate inflammation, fat storage, and other important processes, with possible health consequences. Another system, lipid numbering, is limited to giving only two key pieces of information: the total number of carbons in a fatty acid, which is listed first, and the number of double bonds it contains, which is listed second, after a colon. Under this system, palmitoleic acid is described as a 16-1 fatty acid because it contains 16 carbons and one double bond. The downside of this system is that it's ambiguous, since multiple unique fatty acids with the same number of carbons, but with a double bond at different positions, could have the same name. However, the system is advantageous because it allows us to recognize at a glance how long a fatty acid chain is, whether it's saturated, and if not, how unsaturated it is. There's also delta notation, which is used to identify the position of double bonds in the fatty acid chain. In this system, we return to counting normally, so starting at the carbonyl carbon, just as we do under the IUPAC system. To return to our familiar example, palmitoleic acid would be said to have a delta 9 bond, with the 9 shown as an exponent on the delta symbol. We can now see that there are many ways to describe the structural features of a fatty acid, including the number, position, and orientation of double bonds.